Thanks for attending this talk. My name is Udit, and today Sam and I will be presenting DeepRecSys, a system for optimizing at-scale neural recommendation inference. In this talk, we will provide hands-on demos on how to use the DeepRecSys framework, which has been recently open-sourced. Personalized recommendation is the task of recommending new content to users based on their personal preferences. We start with a large set of candidate items that could be served to the user. These items are then ranked with deep learning-based recommendation models. And finally, a top few items are then served to the user. These recommendation systems are run at a tremendous scale in data centers. For instance, production scale recommendation systems must meet strict SLA targets while ranking hundreds of thousands of items with large scale models with billions of parameters serving billions of users worldwide. Because of the scale, recent work has shown that recommendation accounts for over 80% of all AI inference cycles in Facebook's data centers. As a result, it is crucial to improve the efficiency of neural recommendation inference. However, we find significant heterogeneity across recommendation use cases, which requires automated tools and flexible systems for optimizing this key workload. First, recommendation models are deployed across many use cases such as social media, search, e-commerce, and entertainment. Each of these use cases has a different SLA target in order to preserve user experience and the quality of service. Furthermore, we find each of these different use cases leverages a different type of recommendation model with unique performance characteristics. Second, in addition to the diversity across use cases, we see a rapid evolution of recommendation models being used. Here on the y-axis, we see the number of unique recommendation training flows has increased by a factor of 7x over just 18 months in Facebook's data centers. This increase demonstrates that recommendation models significantly evolve over time, and new ones are always on the horizon. Third and finally, in addition to the algorithmic diversity, we find significant hardware heterogeneity in the data center. Data centers not only comprise various types of server-class CPUs with different microarchitectural features, but due to the Cambrian explosion of specialized hardware, also comprise AI accelerators. Now, given the scale of recommendation in production data centers, it is crucial to design solutions that can enable efficiently using all available hardware resources for recommendation inference. However, when we look at this space, we find a lack of tools to study solutions that can exploit the unique characteristics of the key workload and efficiently deploy a variety of recommendation models with different SLA targets across heterogeneous hardware. To tackle this question, in this talk, we present DeepRecSys, the first infrastructure and scheduler to optimize the runtime performance of end-to-end at-scale neural recommendation inference. The infrastructure first implements a load generator that samples query arrival and size distributions based on characterizations of production data centers. The load generator then produces queries that the scheduler determines how to process in order to maximize latency-bounded throughput, or inference QPS. For example, the scheduler can send the query to be run on an accelerator, or the scheduler can determine to split the query across many CPU cores. Finally, these queries are processed by a variety of neural recommendation models. In our ISCA 2020 conference talk, we show how this proposed infrastructure and scheduler can be used to characterize how parallelism tradeoffs of processing recommendation inference queries on CPUs and accelerators varies across the different models, SLA targets, and input query patterns. The proposed scheduler can achieve 2x performance improvement on CPUs exploiting data versus thread level parallelism, and 5x in the presence of GPU-based AI accelerators. The optimum hardware platform for power efficiency varies across recommendation models. And finally, we show that when we deploy the proposed scheduler in a production data center, we demonstrate a 1.3x performance improvement on CPUs with real shadow traffic. In this talk, we will present the open source DeepRecSys implementation by stepping through each key component that can be extended to study a wide variety of recommendation use cases and optimization opportunities. First, we will provide a hands-on demo on how to use and extend the collection of recommendation models provided. Second, we will show how to run the recommendation models on different hardware platforms, including CPUs and GPU-based AI accelerators. Third, we will show how to instrument the recommendation load generator to study different input query patterns. Fourth, and finally, we will show how the scheduler can be used to trade off parallelism opportunities on CPUs and offload queries to accelerators in order to maximize latency-bounded throughput.
All right, so first, we look at the collection of recommendation models. So in this slide, we see the general model architecture of these deep recommendation systems. Starting from the bottom, we actually see that there's two types of inputs. Continuous inputs, which we know and are really familiar with already, they are processed by these dense DNN feature stacks. And categorical inputs, which are sparse and irregular multi-hot encoded vectors, which are transformed to lower dimensional feature vectors using these embedding tables. Next, after pulling these sparse features, there's a feature interaction layer which combines the outputs of this DNN stack with the sparse features we get from the embedding tables. After this feature interaction layer, we have a predictor DNN stack which outputs the click-through rates, which are the outputs that we want in the end. Note that each of these highlighted components can be configured to implement different types of networks. And by this configurability, we see this in this slide over here, which in DeepRecSys, when we say that we study 8 different industry representative neural recommendation models, which are used in applications such as search, social media, e-commerce, and online entertainment by companies like Facebook, Google, and Alibaba, we can actually classify these models into 3 key classes, which are embedding dominated, MLP dominated, and attention dominated. In each of these 3 key classes, the components that we talked about earlier, they can be configured by their size, the number and amount in which they appear, and also how these components interact. So for example, in these embedding dominated models, there are lots of embedding tables in which each embedding tables has different large amounts of lookups, whereas MLP dominated models are dominated by these DNN stacks that are larger. And attention dominated models have feature interaction layers which are controlled by these attention modules. So let's show a hands-on demo of these recommendation models. So now we're here in this DeepRecSys repository, and let's go to the models subdirectory. Within this model subdirectory, there are 2 different types of files. The first type of file that we want to look at are these model implementations. For example, there's the Deep Interest Network by Alibaba and also DLRM by Facebook, in which there are some differences within these model implementations as shown before. So for example, within DLRM, we can actually see that the feature interaction layer is by default a concatenation, meaning the outputs of the DNN stack and the outputs of the embedding vectors are actually concatenated before putting in through the later DNN stack. Whereas for Alibaba's DIN, the deep interest network, the feature interaction layer is using the attention unit. So in here that you can see that there's differences within this is just one of the differences that you can see within the feature interaction layer. Within all of these models, there's a create model function that ultimately creates this model, and then there's a run function that allows you to feed these models with inputs. So the second type of file within the models directory is the configuration folder, in which we've kind of talked about. For example, in the multitask wide and deep folder, we see that we can configure the size and dimensions of the DNN stacks, such as the MLP bot, MLP top, and also the number of embedding tables and the size of embedding tables. There are also other factors that are really important to the performance and system operations of these models, such as the embedding vector size, in which we set at 32 here. So with all these different configurations, we actually see that the runtime bottlenecks, they're obviously going to be different. So in order to find out how these bottlenecks are different, we have experiments directory. within this operator breakdown folder, we see the sweep script. This sweep script will have a sweep command in which you set the model configuration file, and you sweep a batch size of your choice of granularity. In this case, we've set in powers of 4 from 1 to 1024. And after sweeping all these models at different batch sizes, you will see a result like this. Which is really similar to this graph that we see in the paper. As expected, across the different types of recommendation models, we see a diverse set of operator breakdowns. And this imposes a really interesting, diverse collection of system bottlenecks that must be collectively optimized for improving performance for recommendation models. In this graph in the paper, we see that the results for a batch size of 64, but in our script that we see earlier, we can actually configure the batch sizes in which you want to run this experiment for. Next, let's look at how these models can be run on different hardware platforms. Best way to do this is to show a direct hands-on demo. So, within the models directory that we showed earlier, we actually see that within this test run script that shows out a lot of the functionalities of these models. For example, there are CPU experiments and GPU experiments. For this repository and these models, we've actually devised a use GPU flag that lets you offload the computation of the model onto AI accelerators, or in this case, a GPU. So in order to see the performance differences of running these models on accelerators like GPUs, we have an experiment to show the results. The experiment that we want to see here is a speedup experiment, in which the sweep command is similar to the one we've seen before. Right now we have runtime command configuration for CPU and one for GPU, where the difference is this GPU flag. By using this GPU flag, we're able to see a result by running the script that looks something like this. So in this case, we've run on the Skylake machine, and here are the different total execution time speedups that we see from running these different models. So just from this plot alone, we're actually able to see that some models, such as wide and deep, which are MLP dominated, have greater asymptotic speedup when using an AI accelerator over a CPU. Whereas others, which are embedding dominated, like RM1, don't see much speed up. Something else that's also quite interesting is that the inflection point, i.e., when the model actually outperforms when the model running on this GPU outperforms the model running on a CPU, also differs by the model itself. And this type of experiment, you can run it with different hardware platforms and also whatever algorithm that you want to choose. A byproduct of running this experiment, the sweep-RT experiment, runtime experiment, is that there's also a generated characterization folder in which you're able to see, for example, if I want to see the GPU data running multitask wide and deep, I can see in terms of total execution time for a batch size of 1 milliseconds, and also if we break down the total execution time into model computation and also data loading, in which we actually see that for GPUs, data loading actually becomes a large bottleneck.
Next, we see how the recommendation load generator can be used to study different input query patterns. The load generator produces queries by sampling 2 distributions based on a characterization of Facebook's production data center. First is a query arrival pattern, which follows a Poisson distribution. Second is a query size distribution. In fact, when studying production recommendation services in Facebook's data centers, we found that the distribution of query sizes is an important factor in system optimization. Note that here, the query size, or the working set size of inference requests, refers to the total number of candidate items to be ranked. Here in red, we show the histogram of query sizes in Facebook's data center. We find that the query sizes have a long, heavy tail distribution, even in comparison to log normal distributions shown in blue over here. More generally, we find that optimizing for different query size distributions is crucial for system design. In fact, in our experimental results, we find that in order to optimize system performance or inference QPS under strict SLA targets, we must take into consideration these different query size distributions in order to trade off data versus thread level parallelism on CPUs and offload large queries to specialized hardware. To study these trade-offs and optimization opportunities, we first look at the recommendation load generator. Within the DeepRecSys repository, the load generator is implemented as its own component. As we mentioned earlier, the load generator samples two distributions. The first is for the arrival rates, which follow a Poisson distribution. And the second is for the query sizes, which can be configured to follow a normal distribution, a log normal distribution, a fixed size, or an arbitrary distribution based on your own recommendation use cases. To see the impact of these distributions, we have provided an experiment specifically targeting the recommendation load generator. Here we study the impact of two distributions for query sizes. The first is a normal distribution with a mean query size of 165, similar to the Facebook production data center characterization that we saw earlier. And the second is a log normal distribution with the same average query size of about 165, however, with a much heavier tail distribution as compared to the normal distribution. Note that in both cases, the input arrival rate follows a Poisson distribution with an inter-arrival time of about 5 milliseconds. If we run this experiment and we wait about 5 minutes, we find, as expected, that the tail latency for query sizes following a log normal distribution is significantly longer in terms of P95 and P99 as compared to the normal distribution. Finally, here we look at the recommendation scheduler. First, we consider parallelism opportunities of the scheduler by splitting individual queries to be processed across multiple cores in a server class CPU. Let's first take a look at an example where the scheduler processes a query size of 1024 candidate items. If the scheduler determines the per core query size to be 1024 as well, this means that the entire query is processed on a single core with high data level parallelism and low thread level parallelism. Alternatively, the scheduler could set a per core query size of 512 to split the query over 2 cores. Or with a per core query size of 256, the query is processed on 4 cores with higher thread level parallelism and lower data level parallelism. In our experimental results, we find that this trade-off between thread level and data level parallelism must be carefully managed for each use case, but doing so can offer significant performance advantages. In addition to trading off thread versus data level parallelism, the scheduler can also offload queries to the accelerators. Recall that query sizes in production recommendation services do not have a fixed size. In fact, in some cases, they follow a heavy tail distribution. In order to exploit this distribution in the context of AI acceleration, the scheduler can offload queries higher than a specific threshold to the specialized hardware. Once again, this threshold must be carefully optimized and set for each recommendation use case. However, optimizing this threshold, we find can accelerate the largest queries and unlocks significant performance improvements as well. To explore the scheduler's trade-off, let's take a look at an example. Within the DeepRecSys repository, the scheduler is found across both the load generator and the scheduler file itself. First, within the load generator, we see how the scheduler sends queries to be processed on the accelerator versus multiple cores. For example, if the query is above a determined threshold, it is offloaded to the AI accelerator. However, if the query is below the threshold, it is processed across multiple CPU cores. The query is split across the cores into equal chunks based on the predetermined per core query or batch size. Both the accelerator threshold and the per core query or batch size are set by the scheduler itself. To maximize inference QPS under strict latency targets, the scheduler gradually increases the input arrival rate of queries. Once the measured tail latency exceeds the target, the scheduler backs off. Repeating this process, the scheduler is able to reach steady state. The scheduler leverages a similar hill climbing approach to optimize the accelerator offloading decision and per core query size. Note that here we only consider offloading queries to a single accelerator. To support future accelerator-based systems, the accelerator inference engine enables flexibly integrating other real or emulated hardware platforms. In particular, we estimate the execution time to process each query based on the model, query size, and hardware platform. For realistic end-to-end execution, we include data communication over PCIe, for instance, as well as inference time on the hardware itself. This is based on the predict execution script found within the accelerator directory. For our experimental results, we studied the performance of an NVIDIA 1080 Ti GPU. To see the impact of scheduling across both CPU cores and the accelerator, we provide an experiment targeting the scheduler itself. Here we configure the scheduler to optimize the inference QPS for wide and deep with a strict SLA target of 25 milliseconds. The query sizes follow the log normal distribution that we saw earlier. In terms of the per core query sizes, we swap a range from 512 down to 32. We sweep a similar range for the accelerator threshold ratios, but with a coarser granularity as we see here. In the first experiment, the scheduler only optimizes on CPUs, while in the second, it optimizes over both CPUs and GPUs. If we run this script and wait a few minutes, we find that the optimum per core query size for wide and deep here is 384, where it achieves an inner arrival rate of 13.85, or roughly an inference QPS of about 70. In the presence of an accelerator, we find that the optimum query size threshold to offload to the accelerator is 128, and as expected, it achieves significantly higher throughput, with an inner arrival time of about 6.25 and more than doubles the inference QPS. To recap, in this talk, we presented the open source DeepRecSys implementation with real demos on each key component of the framework. The framework can be extended to optimize new models, propose new scheduler designs, and quantify the impact of new accelerators on data center scale recommendation. If you're interested in further learning about DeepRecSys, you can also watch our ISCA conference talk. We show how the system enables trading off parallelism opportunities across various use cases encompassing models, SLA targets, and input query patterns. We demonstrate how the proposed scheduler provides a 2x performance improvement on CPUs and 5x in the presence of AI accelerators like GPUs. In terms of power efficiency, we find that the optimum hardware platform varies across the different model architectures. We hope that you will join the ISCA Q&A session on Wednesday, June 3rd. And with that, we will conclude this talk, and thank you for listening.